Okay, I want to take this idea of the instantaneous rate of change a step further now. And on screen we've got our, if I just explain what we've got here, we've got the function, the blue curve is y equals x squared. We're going to work with that as an intro curve. And I've got the point A here, and this is where the instantaneous rate of change, and we want to study that. And I know we've been looking at that, getting in closer to A and working out what the gradient of the line is between A and really close to A, and then saying, well, that's a pretty good approximation for the tangent at A. So you can see here I've got the point A, there's a tangent, and this sort of goldy line here, that's the tangent at A. And the information here, the coordinates of point A are 3, 9, okay, that's on y equals x squared, so that makes sense, 9 being the square of 3, and the gradient at the tangent to A is 6. That's been measured by this piece of software, so good for you, that's great. Now what I'm going to do, you can see I've got a point B up here as well. Currently over here I've got the information about B, it's at 5.274, blah, blah, blah. The gradient of AB is 8.274, that's reflected in this little triangle. And the gradient, I'm not interested in the gradient of the tangent of B. So I'm just interested in this 8.274 and getting closer to the gold tangent at A, which we're told has a gradient of 6. Okay, so we drag in, and as you can see, what happens as we get closer, as B gets closer to A, that gradient gets closer to 6. Right, as we get closer, this is where we are now. Look at B, B is 3.073. Right, so now we're measuring the gradient between 3.9 and 3.073, and we're getting 6.073. Pretty close, but we can go closer, can't we? Go closer. We get in there. We're at, actually it's right on 3.9 now, so I've bunged it straight on top. It's at 3.064. So that you get the idea there that we're just getting in closer. I can only do so much with my little stylus pen here. That's about as close as I can get without bunging it straight on top of A. So this is the process that we've been looking at. We started out by looking at an average rate of change between A and B, and now we've really started to concentrate on our attention, now all our intellectual energy on trying to get a really good approximation to the gradient of the tangent at A, because that's called the instantaneous rate of change at A, and opens up this big new field of exciting maths called calculus. Now let's get into the notes. The heading here is we're now moving into finding the gradient function, or the derived function, the derivative. Right, and so we'll build up to this. So what I'm going to do is start with we're going to start with y equals x squared, and we're going to use that as our start function here. Y equals x squared does something like that. So this is y equals x squared. And we're going to go back and have a look at, I'm going to pinch a couple of points. I'm just going to, let's take 3.9, just like we did with the other. This is nowhere near 3.9, but forget the scale of this. It's not of no interest. That's 3.9, right? So we want the instantaneous rate of change at this point, A. So we want, our aim, that's a smarter word, isn't it? Aim is to find the instantaneous rate of change, instantaneous rate of change at A. Right, now this is not new, we've been dealing with this for a bit, so we've been drawing, let's get a little tangent in there at A, that's what it is. Okay, and what we've been doing is we've been getting in really tight to A, haven't we? So what we've done is we've gone, okay, well let's get in it really, let's zoom in here on A, and remember the black is y equals x squared, isn't it? So another point on A that's really close, sorry, another point on y equals x squared that's really close, let's get in there, and that's 3.01, and it's 3.01, I've already calculated this, it's 9. I'm not doing this in my head, 9.0601, right, and then what we've done is we've drawn a little tangent between those two. Sorry, not a tangent, I'm using the wrong words. So the purple is the little segment that joins 3.9 to this, to 3.01, 9.061, and we measure the gradient of that purple line. All right, we've gone in here and we've gone, right, m equals, and then it's 9.061 minus 9, so it's 0.0601, 0.0601, that's the rise over the run, which is 0.01, and that gets us 6.01. Right, now we've been, we looked at it before, we know that actually the gradient of the blue line is 6. So the purple line is 6.01. That's pretty close, and that's what we've been doing, the approximation. If we went in even closer, zoomed in even closer and picked out a point in there even closer to A, and said, well, let's use that one. That's the point 3.001. That gets us 9.006. Right, let's find the gradient of that one. Again, I need a little line in there, a little stumpy line. And if I charge in and find out that gradient, this is getting really messy. But now it's 0.006 over 0.001, and actually that's 6.001. But to 2 decimal places, that is 6. So you can see, the closer we get in, the closer we're getting to 6, and it gets ridiculous, doesn't it? We're just getting in really, really tight now. But that's our aim, find the instantaneous rate of change at A, and that's been our method so far. We're going to take it a step further. We're going to draw this up again, and rather than use 0.01s and things now, that's x, that's y, still working with y equals x squared, and we're still working with the 0.39. But now, rather than talking now about bringing out, let's go out 0.01, let's just give ourselves a little bit of distance. All right, and let's say what I'm doing here is I'm not coming out 0.01, I'm coming out h. I'm coming out h, and our little friend algebra comes into play now, doesn't it? Might just get rid of that 3/9 in the way. We know it's 3/9. I'm going to get on this side. 3/9 is that point there. Okay, now in here is h. Right, they're going to come out h. So I've got my x coordinate there is 3. My x coordinate here is 3 plus h. Okay, so what that means is at this point my y coordinate is 9, and at this point here my x coordinate being 3 plus h, my y coordinate is 3 plus h squared, isn't it? Okay, because this is the rule on this curve is y is the square of x. So if I'm saying that this is the point 3 plus h, then sorry, for x, if this is the x coordinate at this point is 3 plus h, then the y coordinate is 3 plus h all squared. So they're my coordinates for that point. 3/9 is my coordinates for that point. So if I now measure what the gradient of this line is that joins those 2 points, if I measure that gradient, my gradient is 3 plus h squared. I'm going to so y2 minus y1, so it's 3 plus h squared minus my y coordinate here, which is 9, over my x coordinate. So my x coordinates go 3 plus h minus 3. All right, so we need to work this out. That needs to be expanded. I'll do that for you. It's 9 plus 6h plus h squared minus 9 over h. All right, so let's work this out. The 9's cancel on top. So on top I've got 6h plus h squared, and underneath I've got h. So this is my gradient, remember, where I'm looking at this little distance here. Rather than being 0.01 or anything like that, we're making it h. Right, let's just see what happens here. Now if I cancel my h's, I've got an h there, I've got an h there, I've got an h there, I actually end up with 6, look at that on top, 6 plus h. That's what I end up with, 6 plus h. So 6 plus h is my gradient. Oh, that's interesting, isn't it? Now, what is our goal with h? Our goal is to make it as small as possible. In fact, our goal is to make it as close to 0 as possible. So if we say, all right, let's take h to ridiculously small values, so close to 0 it's not funny. Actually, what happens then is our gradient gets closer to 6. So that is the crucial component here, and this is where we start to bring in some calculus. We're now bringing in this concept of a limiting value. A limiting value of 6 plus h, as h tends to 0, is 6. And so we then conclude that the gradient at this 0.39 is equal to 6. Okay, so we've got that, and that's great. We're now getting a little bit more sophisticated with our work. We're not taking these 0.01s and being, getting into that sort of stuff so much. We're looking at h. And that seems to be a little bit more sophisticated and smart, doesn't it? Okay, so just hold those thoughts. What we're going to do now is go one step further and say rather than having a 0.39, let's just have any old point. Still y equals x squared here, still that. But let's have any old 2 points. So this point here now is x, any old x, and if it's x for the x coordinate, it's x squared for the y coordinate, because this is still the square of this. Right, and then up here is another point, and we're still going to make this distance h. Right, that distance there is h. So this is going to be x plus h. Right, that's going to be my y coordinate, and so that's going to be my x coordinate. My y coordinate is going to be the square of that, x plus h squared. So they're my coordinates, and they're completely general coordinates now. I'm not up here. I was using 3,9 as one of my points. Now I'm just using x and x squared. Again, let's measure the gradient of that line. So my gradient is equal to right, as x plus h squared. My run is x plus h squared minus x squared over x plus h minus x. Okay, expanding this out, x squared plus 2xh plus h squared minus x squared. I just expanded that out nice and quickly over h. And again, we've got x squareds cancel up top, so I end up with 2xh plus h squared over h. And when I cancel my h's, h gone, h gone, h gone, I end up with 2x plus h. Right, now let's just reconsider what we're doing here. I've now got a gradient which is 2x plus h, and obviously the gradient will depend on what this value of x is. Now up here the value of x was 3, so that was 2 times 3, 6 plus h. Now this is going to be equal to, as h tends to 0, it's going to be equal to 2x as h tends to 0. 2x as h tends to 0. So what that means now is, I've got, for y equals x squared, I've got what's called a gradient function, and that is 2x. This is the gradient function. Gradient function for y equals x squared, and it's 2x. The reason it's called the gradient function is it delivers the gradient at any point x. So if this is the point 3,9, then I put 3 in for x, and I've got a gradient of 6, and we saw that in the previous example. But if I want to look at y equals x squared, I want to look at another point. Let's just take y equals x squared here. Let's go over the other side of the page and pull out this point here, which is, let's say that's minus 4, 16. What's the gradient of the curve at that point? What's the rate of change there? Right, there's our tangent. What is it equal to? M equals what? So I've got a gradient function though. It's 2x for y equals x squared for that function. Remember that function and that function alone. So my gradient function is 2x, so all I've got to do is sub in minus 4. So m is equal to x, which is equal to 2 times minus 4 at the point minus 4, 16, which is equal to minus 8. So my gradient here is minus 8. So the rate of change at that point is minus 8. That's a powerful thing. We found the gradient function, or another word for that is the derivative of 2x is x squared. Okay, we're up to 13 minutes now. I realise this is a long clip, but we've got one more thing to look at before we go, and that is we've had a look at 3 scenarios. One that we were familiar with, one where we brought an h in and reduced it back to 0 and looked at that limiting idea. Then we discarded with the specifics about this point here, and we said, all right, let's make it x squared. But we're still dealing with, excuse me, the specific function y equals x squared. Got the gradient function for that, but what about the gradient function for any curve? All right, this is big. So let's try, well, it's also wobbly. Let's try and establish something here. Very exciting. All right, so this is now any function. any function, y equals fx. Okay, and again we're going to go from the point down here, x. Right, but that's now, right, that's now, I'm sorry, I don't know what I'm doing here. I'm just taking any point x, and I'm going to take any other point, h along here, so that's h along there. So now I'm at this point here, which is x plus h for the x coordinate. This is my x coordinate down here is just x. I'm keeping that coordinate there as x coordinate x. What's the y coordinate though? Well, it's whatever the function value is at x. Excuse me. And what's the function value at x plus h? Well, it's f of x plus h. So there's my, and what I'm doing is joining them up, and I'm finding out what the gradient is. So what's the gradient here of that line? Well, the gradient is equal to f of x plus h minus f of x. So that function value minus that function value, which just gives us, if you like, there's f of x plus h, this is f of x, this is f of x plus h, so that gives us our rise, and our run is h. Now if we find the limiting value as h tends to 0 of that, then what we have is our gradient function. Therefore, our gradient function, in general terms, for any function is that as h tends to 0. Or another way of writing that, gradient function or derivative is f dash x. F dash x is my derivative function. So, and I could write it, more customary to write it like this. The limit as h tends to 0 of, now this might at this point become a little bit strange and a little bit scary. Don't worry, we'll spend some time on this and get it right. But I'm going to close there, and we will have a chance to discuss this in class. See you soon. Okay, so I just wanted to show you one more thing. I know it's a long YouTube. I don't like making this long, but I really need to show you an example of how this works. So if we have a look at an example now, so find f dash x, or the derivative function, for f of x equals x squared plus x. Okay, so it's really important we have a look at this example, even though it might at this stage, or will, be very difficult for you to follow. So what we're going to say now, therefore, is that f dash x is equal to this limiting function that I've got up here. So the limit as h tends to 0. Remember, we're just looking for the gradient function. Right, so I'm just writing this out to start with, putting that over h. Now what I'm going to do is work out what each of these things are. So f of x plus h. If f of x is x squared plus x, then f of x plus h will equal x plus h squared plus excuse me, x plus h. So that's x squared plus x. Okay, we're putting x plus h in for x in each of these places. Remember from your function work, x squared, I'll just expand that, that's 2xh plus h squared plus x plus h, which is x squared, oh, that can't be simplified, can it? Okay, so we leave that as it is. F of x is as it stands. So this f of x plus h reads x squared plus 2xh plus h squared plus x plus h. Now we're going to subtract x squared plus x, which is, when we subtract the whole thing, x squared minus x. Put that over h. There will be some simplifying to be done here. So the x squareds cancel. See that? X squared cancels with that. 2xh, I've got plus x minus x. Excuse me. So I've got 2xh plus h squared. Remember, that's gone with that. My plus x minus x gone. 2xh plus h squared plus h over h. Now before we sub in h equals 0, I need to divide through by h and get rid of the denominator of h. So I've got 2x plus h plus 1. once I've run my division of h through, 2x plus h plus 1. Now I can run my h equals 0 through and I get 2x plus 1. So this is my derivative function, my gradient function. That's my gradient function for y equals x squared plus x. So for this x squared plus x, which looks a bit like x plus 1, I think we're doing something like this. For that function there, its gradient can be determined at any point by applying this gradient function 2x plus 1. So at the point, so therefore, say at x equals 3, gradient equals 2 times 3, which is 6, plus 1 is 7.